What now? Okay. So the talk would be on reconstruction of circuits, a specific model of circuits called homogeneous depth-3 circuits. It's a joint work with Neeraj, who already defined the reconstruction problem, but just to make sure we are on the same page, let me go over it again. That let f be an n-variate polynomial of degree d, and suppose it can be computed by a circuit of size s, yeah, from a class C. And the reconstruction problem is the following: given black box access to f, output a small circuit from C. Yeah, black box access means membership query access, that you give a point to this black box and put the evaluation of f at that point. So ideally, we want the size of the output circuit to be polynomial in S. S is, let's say, the size of the minimum circuit computing f. And we would also like the output circuit to come from the same class C. So this notion is called proper learning. And further, something to do with the efficiency of the algorithm. Ideally, we would like the learning algorithm to run in time polynomial in S and D. But even if the running time is polynomial in the dense representation of f, which is like polynomial in this big N, the number of monomials in N, it can still be non-trivial, because a trivial algorithm will have to go over all possible sizes circuits, which is exponential in S. It can be much larger than the quantity n when S is between small n and n. Okay, so unfortunately, reconstruction turns out to be a hard problem. It is at least as hard as lower bounds because of the following results. The first one is by Fortnoy and Clivans from 2009, who showed the following: that a randomized polytime reconstruction algorithm for a circuit class C implies explicit lower bounds for the same class C. Yes, in particular, it will show the existence of a function from BPEXP, the exponential time version of BPP. And Volkovich has a sort of a de-randomized version of this result, where starting from a deterministic polytime algorithm, you get an explicit function in EXP for the same class. So it's at least as hard as lower bound. So naturally, people focused on reconstruction algorithms for those circuit classes for which lower bounds, non-trivial lower bounds, are known.
And these are Boolean circuits?
No, arithmetic circuits.
This works also for arithmetic circuits?
Yeah, also for arithmetic circuits.
And the same result for Boolean circuit?
Yeah, for the Boolean circuit, I think it's they talk about pack learning here instead of exact learning. I mean, for this talk, all circuit classes would be arithmetic circuit classes. So there's a slight difference between. Okay, so naturally, the converse question is: does lower bound imply efficient learning? Seems unlikely, because reconstruction is an inherently hard problem. It's directly related to approximating the minimum circuit size. The minimum circuit size problem, or the MCSP problem, is quite well studied, but it's not as well understood for Boolean circuits. And it's the following problem: that given a truth table and an integer s, check if there is a function computed by a circuit of size s that's defined by this truth table. Now, this is, of course, believed not to be in P, but it's not clear whether this is NP complete. But what is known from a result by Allender and Hirahara is that even an approximation version of the MCSP problem is probably hard. Hard in the sense that it's not in polytime. So here is the precise result: that let epsilon be some small constant, or it can be really small, much smaller than a constant. Then approximating the minimum circuit size within n to the 1 minus epsilon factor cannot be done in polynomial time, assuming one-way functions.
This result is just for the Boolean case.
Yes, this is just for the Boolean case.
So
talking about just.
I'm not sure that there's any.
Yeah, nothing for arithmetic circuits. Yes, yes. So I was coming to it. So as Russell pointed out, it's for Boolean circuits, not for arithmetic circuits. But we'd like to draw an analogy between the Boolean and the arithmetic world, and would like to say that, okay, it seems like reconstruction is also hard, even if f is given verbosely as a list of coefficients So that's the analogy between truth tables and polynomials, verbose representation of polynomials.
Oh, so you don't have but analogous result, it's just an analogy.
It's an analogy, yeah. So by analogy, it seems like learning arithmetic circuits is also hard. Right, so but this doesn't rule out the possibility that certain kinds of lower bounds, like natural lower bounds, might still imply efficient learning. And in yesterday's talk, Marcus already went through natural proofs, which was proposed by Razborov-Rudik, and the algebraic versions by Mike, Amir, Volkovich, Ben Volk, Joshua, Minal, Mike Sachs, and Shubhangi. And so one interesting feature of natural lower bounds is the constructivity feature, which already gives a headway towards efficient reconstruction, that inside the lower bound there's an efficient algorithm which is at least able to recognize the fact that f has low circuit complexity. Right? Given the list of coefficients of f, it would output 0 if f has low complexity. So it's kind of a separator for this class C. The question is whether one can strengthen this or build on this kind of separator algorithms and turn it to a full-fledged learning algorithm. Now there are several success stories coming from the Boolean circuit world, starting from the seminal celebrated work by Lineal, Mansour, and Nizan, who used the natural lower bound framework for AC0 circuit to give pack learning algorithm. But let me start from the most recent one by Carmosino, Impagliazzo, Cabinets, and Kolokolova, who used the natural lower bound framework for AC0P circuits to give quasi-polynomial time pack learning algorithm for the same class. And the earlier two results, the one for AC0 and AC0 with polylog majority gates, they are also pack learning quasi-polynomial time algorithms. But let me make a note that these learning algorithms are not proper in the sense that the output, let's say for this, is not an AC0 circuit, but some quasi-polysize circuit. And same for this one as well as this one. Okay, so the natural next question is like, can we hope to get such natural lower bound to reconstruction translations for arithmetic circuits? There are some favorable results in the arithmetic world by Clivanch and Amish Pilka and Mike Forbes and Amir, who gave efficient reconstruction algorithms for models like ROABP and non-commutative ABP, set multilinear ABP, and so on. And these models do have natural lower bounds. So, and the learning algorithms are also efficient. So that makes one quite hopeful about it. But in the arithmetic world, there are several other models for which natural lower bounds, really strong lower bounds, are known, but no learning algorithm. So it's not clear what the status is. The reason is like there are a few challenges in the arithmetic world. The first challenge is like we have to do exact learning for arithmetic circuits. And pack learning wouldn't make too much sense here. The reason being two polynomials differ at far too many points. So if the output is actually an arithmetic circuit, so it's computing a polynomial, so it has to compute it exactly. There are two other challenges, depth reduction and homogenization. So let me briefly state here what are the issues here, and then I'll take up an example to explain these points more. The first issue is depth reduction. Here even constant depth circuits are far more powerful. And the second issue is homogenization, which makes reconstruction challenging even for classes for which exponential natural lower bounds are known. So let me illustrate these 2 points with the help of this model homogeneous depth-free circuits. That's also the subject of this talk. So homogeneous depth-free circuit computes a polynomial f as a sum of terms, s terms. Each term is a product of d linear forms in n variables. Yeah, we'll call such a circuit NDS homogeneous depth-free circuit. And there are very good lower bounds known for this model. When d is less than n, there's a lower bound shown by Nizan and Wigderson, which is like n to the omega d. Yeah, and even for higher d, like d greater than n, one can show exponential lower bound. So for the whole range of d, like starting from small d to 2 to the n, you have very good lower bounds, and these lower bounds are actually natural. Yeah, so the obvious next question is that, okay, if you have very good natural lower bounds for this model, can we do learning for this model? And this was also posed as an open problem by Clivench and Spilka, that whether we can actually do this. Now, let me state what we have. We have some partial progress, some partial answer to this question, that if n is like omega d square and S satisfies some mild condition, then there is indeed a randomized poly ns time algorithm to reconstruct NDS homogeneous depth-free circuits, but not NDS homogeneous depth-free circuits in full generality, but only non-degenerate, and that's what makes this a partial result. But we do proper learning. The output is indeed another depth-free circuit, homogeneous depth-free circuit, and not an arbitrary circuit. But there are two obvious restrictions, right, that makes it a partial result. One is the degree restriction, which is that n is larger than d square, and of course the main restriction, which is the non-degeneracy restriction. I'm going to explain more what this is in the next slide. But let me quickly say that we can ignore this for the moment. Let's not pay too much attention to this. The reason being that we do feel that this restriction is a technical artifact coming from our proof, the way we are arguing it, and this shouldn't be there. Like, I mean, if with some other kind of proof technique, it should be possible to do it even for larger d. And the underlying main reason being that we have good lower bounds for a large range of d. So this doesn't quite make sense. So ignore it for the time being. So this is the main restriction. So the non-degeneracy condition is the following. That recall that f is computed like this. Yeah. So let k be this quantity log s by log n by d roughly, and u be the kth order partial unitary space of f, and ui be the space spanned by the kth order partials of ti. Right. So then it's obviously clear that u is contained in the sum of these ui's. The non-degeneracy condition states, it has two parts, that this sum is actually a direct sum and this containment is an equality. Yeah, of these two parts, we think that this direct sum assumption is rather mild. The main non-degeneracy condition is coming from this equality. Yeah, why this is mild? For example, assume for the moment that S is poly n. If S is poly n, then k is a constant, right? Now, notice that if k is 0, then all this is saying that without loss of generality, I can assume that T1 through Ts are linearly independent, right? So that's saying like the 0th order spaces they form a direct sum, right? So now the direct sum part of the non-degeneracy condition is saying that all we want is that the direct sum condition to hold up to some constant k. Yeah, k0 is like without loss of generality, but we want this up to some constant k. Right, so the equality is the main source of non-degeneracy. Okay, so one can show that random homogeneous depth-free circuit is almost surely non-degenerate in this particular sense.
Is there some monotonicity in this non-degeneracy, that if this equality holds for some k, does it hold for other k's? Smaller, larger?
Larger.
It holds for all.
Yeah.
Wait, no. I mean, you
the other way around, is it?
The base k equal to 0, you said is.
K equal to 0 is without loss of generality. So higher is like stronger, putting stronger restriction. Yeah.
If it holds for some k, it implies the k.
Smaller k also. Yes. Yeah.
Right.
That's correct. Right. So, naturally, like, this doesn't entirely answer the question posed by Clivench and Spilka, and so the question is whether we can get rid of non-degeneracy entirely and completely answer their question. For a moment, if you believe that we are able to do this, let's see what are the consequences, and this will also help me explain those two issues.
Did we hear in the first talk today that this is NP hard or something? No.
NP hard to find the minima, right? A minimum sized circuit. But reconstruction,
Around poly size now.
yeah, so it's like approximating the minimum size. And, yeah.
If you can go back. So this condition, this non-degeneracy in particular, does it apply uniqueness of representation in some sense?
Sorry, this condition, does it imply uniqueness of representation?
Does it imply that you can only write it in some
It does,
unique way
it
of
does.
interpretation maybe?
Yeah, it does, yes. Yeah. So, as I think Neeraj mentioned in his talk, that the proof implies that the circuit that you will get is unique.
The next question is, can you get away with just assuming uniqueness, or you need actually the non-degeneracy?
Good question, but it's not clear. Like just assuming that the circuit is unique, that a unique SI circuit, it's not clear whether we can do reconstruction.
Chandan, is there any hardness rules for this problem for the reconstructing the
Arithmetic circuit, depth arithmetic, hardness result. Yeah, I think that there's one I remember by Clivanch and someone else on, but that was on pack learning under any distribution and not uniform distribution. So they showed the pack learning under arbitrary distribution is hard.
arithmetic circuits?
Yeah, for depth 3 arithmetic circuits.
But not for membership.
Not for and not for uniform distribution.
And for random circuits, for general random circuits, is reconstructing hard or you don't know?
Oh, general random circuit, so not depth 3 or anything. Yeah, it's not clear. Even for depth 4, it's not clear.
So these tensor rank approximations, don't they give some hardness results for these things?
But they'll give it up to a constant, right?
Yeah,
1
so
plus
say that,
epsilon.
if you want to do learning, it will say that your blow up has to be at least this much.
Yeah, because reconstruction allows poly S, right? So you can go. Yeah,
Okay,
so-
poly will be
Yeah, but this hardness result by Clivans, that's also holds for poly S. But that was for pack learning under any distribution. Okay, so some of the consequences are the following. The first consequence is like if you could do the same thing without non-degeneracy, that would imply a lower bound for depth 3 arithmetic circuit, which is not known yet, by a simple homogenization trick that suppose f is computed by an NDS depth 3 circuit, then you can homogenize it, and this homogeneous polynomial would be computed by a homogeneous depth 3 circuit in one more variable, and thus we'll get an efficient reconstruction for depth 3 circuits, which in turn will imply a lower bound for the same class, right? Because learning implies reconstruction, we already saw. Learning implies lower bound, yes.
This low bound would be this weird low bound, right?
But this would be BP-EXP, but this would still be some sort of explicit lower bound, right? That existence of a function in BP-EXP.
Could one expect like title connections?
The title connection is won by Volkovich. Like if you get deterministic, then you can actually compute a polynomial in EXP, a multilinear polynomial in EXP. That's the only thing.
It's not the same as saying deterministic reconstruction implies PIT and then whatever PIT gives.
No. The proofs are along the same line. Yeah, the proofs are quite similar, but yeah. Right. The second consequence is that this will also imply reconstruction for general circuits, and that's because of depth reduction results by several people, starting from Agarwal, Vinay, and Pascal, Sebastian, Ramprasad, Neeraj, Pritish, and Ankit.
Wait, I have a question. In the previous slide, like you'll have reconstruction for some circuit, but it will have a huge degree, like because generically.
Correct. It will have a huge degree, and the degree will still be sub-exponential. It won't be. It would be like n to the root d, and that's what I said. Like you can perhaps ignore this degree restriction. So this seems to be a technical.
So you can get. So you believe you can get. Degree
we believe that the same thing should be possible, assuming just non-degeneracy, but even for much larger d. If you change the proof technique, the template might be the same, but some other means. It doesn't seem to be like a fundamental restriction to us. Okay.
So, can't you just increase n arbitrarily? Or is n not the number of variables?
N is the number of variables, yes.
So, can't you just introduce dummy variables?
But you won't get non-degeneracy might affect by that, right? I don't know actually, yeah.
No, I don't know.
So then it's just polynomial in D as well as N.
But the problem is like when the running time will be increased. Like if
Right.
your S is like
Right, so the running time will have now be polynomial in D.
yes,
But that's
That was already the case.
yeah.
Okay.
Yeah, so I think just homogenizing will probably not do anything with the non-degeneracy condition.
I mean, if I just replace every variable xi by summation yij's and so on, I've got lots of variables,
Yeah.
but something, I don't know what would happen to the, yeah.
Oh, I see, that way, like just to increase the number of variables, okay, if they are too small. Ah, okay. Oh, yeah. So then the non-degeneracy condition won't hold. It will fail.
Why?
Yeah.
Oh,
So, sorry, so you, what are you doing? Okay.
why non-degeneracy will follow?
So not sure I understood the question then properly.
Suppose you just pretend that your polynomial is actually over a larger number of variables,
Okay.
It just doesn't depend.
but it just doesn't depend on a lot of them. A lot of them are just dummy variables.
Yeah. So then that's what I'm saying. Then this condition won't hold. This equality won't hold.
But the spaces are exactly the same, right?
Yeah, spaces are not changed. By adding new variables, it doesn't change not U, not UI.
Some space will be zero, right?
Okay. So let's see. So you're saying that you use lots of dummy variables. Yeah.
so you don't change F at all. You just pretend there are more variables.
Right. Okay.
Well, another way to look at this, you multiply the entire circuit by like Z1, Z2, Z3, Z4, Z5, Z whatever, fresh new variables. And then you look at all these new variables.
Yeah, so that's one way, and this another way is also much simpler. You're saying like those dummy variables are there, but the spaces won't change, right? So that's what you're saying.
They will change, no? Because n is figuring in your k.
N is figuring in my k. Yes.
But it's even making the case smaller, so.
You're taking a smaller shape.
So
So maybe, maybe we'll
Okay.
do this offline, I think, yeah, you should go on.
yeah, I think the answer is reasonably simple. So let me think about it.
It's either yes or no, but.
Yeah. Okay, I'll get back to you. Okay, but so the reason we need this non-degenerate, this condition that n is greater than 3d square is to make this non-degeneracy condition hold with high probability for random circuits.
Okay.
Right? So so otherwise, so that's one. Okay. So right, so it will give reconstruction even for general circuits, sub-exponential time reconstruction, and thus we believe that unconditional translation from natural lower bounds to efficient reconstruction seems extremely challenging in the arithmetic world, even for depth-3 circuits.
What do you mean by natural lower bound?
Natural lower bound proofs.
As in Marcus's talk yesterday.
Oh,
This Rasborov-Rudik and the algebraic versions of it. And if we believe that sub-exponential time reconstruction for general circuits is not possible, then perhaps this translation is also not possible unconditionally. What might be possible though is that we might be able to use this natural lower bound framework of this model to do efficient reconstruction for the same model under some non-degeneracy condition that also originates from this lower bound proof. It's not like a totally random arbitrary non-degeneracy condition. The non-degeneracy condition also arises from the natural proof lower bound, and let me also illustrate this point using our non-degeneracy condition that for homogeneous depth-3 circuit, the natural lower bound by Nizza and Wigderson, the one crucial aspect of it was that each UI is simple in the sense that it's a low dimensional space, and what the non-degeneracy condition is trying to do, it is trying to exploit this fact that UI is simple and translating the reconstruction problem or reducing it to decomposing the space U into these simple spaces. So that's what the non-degeneracy condition, that's how it is helping us. But apart it is not clear how to do this decomposition, whether this is possible at all efficiently. And therein lies the contribution of this work. We show that this is possible. And in doing this, we also propose this paradigm that Neeraj was talking about in the morning, a paradigm for handling large fan-in gates, which appears to be the main difficulty of reconstruction problems. So this is the paradigm in 2 steps. That first we reduce the problem of finding children of a sum gate to a decomposition problem. And in our case, this first step turns out to be quite trivial. It follows directly from the non-degeneracy condition. Right? So you reduce it to this decomposition problem. And the second step is you actually decompose this, do this decomposition by considering a space of linear operators acting on U, and use the structure of U to somehow do this decomposition. And the precise structure that we use is the irreducible invariant spaces of U induced by S. So I'm going to talk about this now in a moment. But that's the template. And as he also mentioned, that we feel that the paradigm do have the potential to give other reconstruction results, as Shubhangi was mentioning, reconstruction for random circuits in general. I'm not sure whether that is possible, but maybe for those models for which lower bounds are known, one might be able to do it, assuming random, the average case kind of stuff. Right. So prior work on efficient reconstruction like ROVP except these models, ROVP, non-commutative AVP, and Reed-Muntz formulas, most of the other models do assume that the fan-ins of the sum gates are very small, either constant or they work only for up to n or n square kind of stuff. So this is a good time to also review some of the related works, just to show why they work with, not why, that they do work when the fan-in of the sum gates are small. Starting with this work by Bimal, Bargadano, Bishotti, Kushelevich, and Vericchio, who gave a randomized reconstruction for symmetric tensors and general tensors. And the same argument Kleivansh and Spilka saw, that this also gives an algorithm, a reconstruction algorithm for general depth tree circuits, but it's no longer efficient, it's exponential in D. These algorithms are not proper learning because the output is an ROVP and not depth tree circuit. Then Amir gave reconstruction over finite fields for depth tree circuits with tau fan in 2. This is a quasi-polytime algorithm. It was extended to like constant fan-in, again over a finite field. And they also de-randomized the algorithm in the process. And then Gaurav gave a randomized reconstruction for depth 3, again with fan in 2, but over reals or rationals, fanning in polytime. Okay, and these algorithms are proper, modular small condition, you can ignore that. There is also one algorithm known for depth 4 circuits under the assumption of multilinearity, and also fan in 2, tau fan in 2, and that's also a polytime algorithm. This is also a proper algorithm. There are a few reconstruction algorithms known assuming non-degeneracy condition. There are a couple for depth 3 powering circuits or symmetric tensors, one by Neeraj, the other by Garcia Marco, Pascal, and Pecate. So the second one, which is more recent, is better than the first one in the regime when D is much smaller than S. So then this is quasi-poly, whereas this is poly. So there are also reconstruction algorithms for more general models, assuming non-degeneracy conditions. One is by Ankit, Neeraj, and Yuming, who gave randomized reconstruction for regular formulas with fan in 2. Regular formulas are formulas where the fan-in of the gates at every level are equal. Earlier this year, we gave a randomized reconstruction algorithm for constant with homogeneous AVPs. Now, let me put the last two results in the context of lower bounds. Remember that we get learning only for models for which lower bounds are known. So far, this has always been the case. Just to put this result in context of lower bounds, that regular formulas do have a super polynomial lower bounds known. And the second one, like Mrinal showed a linear width lower bound for homogeneous AVP. So that's why, I mean, these lower bounds already indicate that these are weak models, so probably you can do learning. Okay, so that's it. We can now go back to homogeneous depth-3 circuit. I can describe the algorithm now. Any questions so far? How much time do I have now?
15 minutes.
15 minutes, okay. All right, so the outline of the algorithm is very simple. That step 1, you compute the basis of U. In step 2, you decompose. That's the main step. And step 3, you find the individual terms from the UIs. So what do you mean by the decomposition? That you, from the basis of U, you find basis of this individual spaces. And everything happens in the black box setting. I might not explicitly mention that this is black box, but it's always black box. Okay. So the first step and the third steps are relatively easy. So let me quickly go over it. That we want to compute a space, a basis of U, and that's because given F, you can compute its derivative in the black box setting, and you do this k times. K being small, you only have to, I mean, the number of elements in this set, the kth order derivatives of F is also small, so you find all of them, and then find a basis of it. That also you can do in the black box because of the second fact. So that's how you do step 1, and at the end of step 1, we get a basis of U. Yeah. So let's remember that this is gamma, and U is a space of dimension M. Okay. Now let's see how to do step 3. Step 2 I'll come later. So, but when step 2 finishes, we already have basis of these individual UIs. Yeah. And let these basis elements be these, right? And now define the set degree k to be the set of all degree k monomials in the underlying set of variables. Yeah. Okay. So now set up these equations, which would essentially boil down to solving a system of linear equations. Yeah. So for every alpha in a degree k monomial, you set this equation up, pretending that these C's are variables, and we have black box access to all the G's as well as the F. Right. So using this, you can solve this linear system just by evaluating the G's and the derivative of F at different points, and you solve for all the C's. Yeah. Once you solve for all the C's, then notice that for every I, right. So this is what would be satisfied. So we are basically using the basis of the UIs to get access to the derivatives of the TIs, all of them. Right? And this is how you do it, because you do it for each and every alpha. And the reason this holds is because, again, because of the non-degeneracy condition, because of the direct sum structure of the UIs. Yeah. So once you solve the CIs, you get the derivative of the TIs for all alpha, and you put them together using this nice well-known formula to get TI, and which holds for any homogeneous polynomial. It doesn't have to be product of linear forms. TI is any homogeneous formula. Yeah. So from the derivatives, you can get the polynomial. Yeah, that's it. So we'd like to thank Gaurav for showing out this precise argument. The earlier argument for step 3 was slightly longer than this. It was along the same lines, but slightly longer. Okay, so now let's come to the main step, which is step 2. For this, I'll quickly go over some basic definitions. So let U be a space and S a space of linear operators on U. We say V, which is a subspace of U, is an invariant subspace if S maps V to V. And moreover, V is irreducible if you can't split it further into invariant spaces, right? Which means that there's no invariant subspace properly contained in V. Okay, we also define closure of a vector with respect to this space of operators S. It's the smallest invariant space of U containing V. Right? That's closure of a vector. And from the definition, it's easy to see that, or not too hard to see that, given a V and a basis of S, because S is a space of operators, a basis you can represent by matrices. Yeah, and given this set of matrices and V, you can just keep applying these matrices on V until it is closed, right? Until you get the space, you can no longer grow, and that gives you the closure of V, right? And this can be done in deterministic polytime, right? So, yeah, that's it. That's the background. So now let's go into the actual decomposition step. So the main idea is to, so far we haven't told you what's the choice of this space of operators. So we choose this space of operators carefully so that these individual UIs, they turn out to be the irreducible invariant subspaces of U induced by S. So the decomposition is unique in the sense it's a unique irreducible decomposition of U. And the second step is you find this decomposition, and the way you find it is that you pick a vector or different vectors in U carefully, such that the closures of these vectors with respect to S will give you these spaces U1 through US. Yeah, that's the idea, and let's see how to make this idea work. You can, of course, you can view this as a simultaneous block diagonalization step. Okay, so the choice of the space of derivatives is the following. So you consider all kth order derivatives, multiply them by kth degree monomials, yeah, go over all possible choices of alpha and beta, yeah, and look at the space spanned by them, yeah, over F. That's the set of shifted differential operators, and S is a subset of them, or a subspace of this space, consisting of only those operators or shifted differentials that map U to U. Yeah, so that's the definition of S, right? And it turns out, and again it's not too hard to show, that you can actually compute a basis of S from a basis of U. Recall that we already have a basis of U from the first step. We have already computed it, and I'm skipping over this. One can, easily, like before, one can set up a system of linear equations and get a basis of this space of operators S. Yeah, so by the end of it, we have a basis of S, and let's see how to use it. But before using it, let me list a few properties of S which will help in the proof. I'm not going to prove any of these, but these are the crucial properties which actually helps in giving us the decomposition. The first is that U1 through US are indeed invariant subspaces of U under induced by this choice of S. And the second is that there exists operator psi having distinct eigenvalues in this space S. And the third claim is a strengthening of the first claim, that not only these are invariant subspaces of U induced by S, these are actually irreducible invariant subspaces. Yeah, so I'm not going to prove these claims. This is where the technical bit goes into. But let us use this to give the decomposition algorithm. How much time?
7 minutes.
7 minutes, okay. So, any questions so far?
So can you give some intuition as to, normally a guess would be that you would take just differential operators would have been enough, but...
Oh, but taking derivatives, the degrees won't match, right? You will take, so it won't be a differential operator from U to U, right? So, yeah, it will take you to a smaller degree differential space. Right, so from the first step we have a basis, and we already know how to compute a basis of the space of operators. Yeah, and these operators can be naturally associated with matrices because a basis of U is fixed. Once you fix a basis of U, you can naturally associate every operator in S with a matrix. Yeah, so these M gamma psi i's are the corresponding matrices. Yeah, so you first pick a random operator from the space. Yeah, just by picking random elements from F and taking their linear combination, yes, and compute the characteristic polynomial of this random operator, factor it completely. If it is not a square free factorization, then you output fail. Yeah, otherwise you factor. Yeah, and so we'll look at the correctness of the algorithm in the next slide. And now you compute null spaces of these factors evaluated at the random operator. Yeah, and provided it's not clear what these null spaces are supposed to give, and pick vectors from these null spaces now. Yeah, any one of them, yeah, from each of these null spaces, and compute the closure of these vectors with respect to your original space S of operators. Right. So, and that's it. That's the algorithm. And these closures are supposed to be our UIs. Right. So that's the claim. Yeah. So let me go over it again. As I go over it, I'll also analyze it. Yeah. So as I said, like this is just picking a random operator in S. And why is that this random operator would the characteristic polynomial of it would be square free with high probability? That's because of the second claim, that there exists an operator psi in the space with having distinct eigenvalues, and one can show that this implies that a random operator will also have distinct eigenvalues, and hence the characteristic polynomial would be square free. Yeah, and now the claim is that the null spaces of these factors evaluated at this random operator, these null spaces are contained in the UIs. Right. So although I've used a slightly different notation here, but this is exactly the space UI. I'm just distinguishing with a different notation because UI is a space of polynomials, and once you fix gamma, this is the corresponding space of vectors lying in f to the m. That's all. Yeah, because these spaces are not spaces of polynomials, but spaces of vectors in f to the m. Yeah, so and that's the main claim, that we have to prove that these null spaces are contained in this Fi. And now it's over, because once you know that these null spaces are actually spaces inside the UIs, you just pick a vector, and if you compute the closure, you're going to get UI, right? Because it's irreducible. Right? That's the third claim, that because they are irreducible, you are going to get the whole thing and nothing more, nothing less. Right? So all we are left with is to prove that these null spaces are indeed contained in the UIs. Yeah. Okay. And that would be the end of the talk. Okay, so let me quickly go over it. That the statement does not quite depend on the choice of the basis. So I'm going to prove it with a easier choice of basis, which is that gamma is found by taking unions of bases of U1 through US. Yeah, and with this, every operator in S would be block diagonal, right? Because the UIs are invariant spaces. So they map UI to UI, so it would be block diagonal. And Pi be the characteristic polynomial of Ri. Right? So that means the characteristic polynomial of the whole entire operator is the product of this, which we know is also a product of this coming from the algorithm. Yeah. So which means that Hj divides some Pi. Yeah. So we are going to show that for this choice of j and I, Nj is contained in the corresponding UI. Yeah. So the choice of I gets fixed here for the rest of the proof. So now pick a vector in Nj. So I have to show that this vector also belongs to UI. Yeah, so apply the polynomial Pi on this operator. It operates like this, and then multiply with the vector v, and it will evaluate to 0. The reason being that Hj divides Pi, and v is in the null space of Hj m gamma. Right? So that's why this left hand side is 0. So this is 0. So you think of V as a column vector, yeah, split it up into S segments, V1 through Vs. The V1 corresponds to the segment for U1 and so on. So you wish to prove, or we wish to prove here, that all the segments here are 0 except Vi. 1 minute, okay, thanks. So I'm done. So yeah, so it's a very simple linear algebra from here. So let me quickly go over it. So this gives Pi Rq times Vq equal to 0 for every q. Yeah, so now pick a q which is not I. You wish to show that Vq is 0, right? And all we have is Pi Rq Vq is 0. So because H is square free, there would be polynomials E1, E2 such that these holds. So evaluate this equation at Rq. This vanishes because PQ is the characteristic polynomial of RQ, and then multiply both sides by the vector VQ, and that's 0 because this is 0 coming from here. So So that means if you choose Q not equal to I, it would be 0. And so the only thing that would be left in V is Vi, which means that V would be in Ui. Yeah, so it's a simple proof. So the summary is that, so we give a reconstruction algorithm, partial answer to the problem posed by Klaivansh and Spilka. And our reconstruction algorithm is strongly influenced by the natural proof framework of Nizan-Wigderson, and as well as the non-degeneracy condition. And in doing so, we came up with this paradigm, which we feel that might be applicable elsewhere. The choice of the space was shifted differential space, and I would like to close with these open problems that can we apply this paradigm to other models like homogeneous depth 4 circuits, constant depth multilinear circuits, regular formulas, multilinear formulas. For all of these models, very good lower bounds are known. All of them are natural lower bounds. So can we apply this and do reconstruction, assuming non-degeneracy? Yeah, that's it. Thank you.
Questions?
So is there a sense why in this algebraic setting we are always getting proper learning algorithms, and somehow, I mean, in the Boolean setting, the difference is pretty noticeable, and here we seem to not see a major difference.
Assuming non-degeneracy we are getting, I think because of the uniqueness of the circuits, but if you don't assume non-degeneracy, then even for depth 3 powering circuits, the learning algorithm gives you an ROEVP, which is much higher.
Okay, so there do exist some problem.
Yeah.
So in assuming non-degeneracy, you actually get the smallest circuit for it. I mean, there's
Yes.
no blow up in size at all.
Yes. Yeah. The proof tells you that the circuit is also unique.
Other questions? Thank Chandan again.
Thank you.
340?
340.
340.